Using resolution of vector, you can even add vectors. For addition of vectors, we have used parallelogram law, triangle law. If we have more than two vectors, then we use polygon law. But instead of parallelogram, triangle, and polygon law, we can use resolution to add more than two vectors. Take this example. So you have three forces which are acting on a point. The first one is F1, which is 10 Newton. The second is F2, which is 5 Newton. And this is F3, which is equal to 1 Newton. This is the angle. Let's say this angle is 37 degree. This angle is 45 degree. Let's call this force as not just 5, it's 5 root 2 Newton. This is 5 root 2 Newton. You're supposed to calculate net force. Calculate net force. Okay, so to calculate net force, you just have to add these three vectors. So the net force F will be its vector sum of F1, F2, and F3. So to calculate net force, you simply have to add these three vectors. You have to add vector F1 with vector F2 with vector F3. This is how we calculate net force. But to calculate three vectors, we can't use parallelogram law directly, because parallelogram law can deal with two vectors, only two vectors at a time. We can't even use triangle law because triangle law also deals with two vectors at a time. So instead of parallelogram law, triangle law, you can use polygon law, but polygon law would be very lengthy. We can add these vectors using resolution. So using resolution, the first step is resolve all vectors along x and y axis. Resolve all vectors along x and y axis. That's the first step. You have to resolve all the given vectors along x and y axis. So this is force F1. The component of force F1 along x-axis is F1x. And this F1x will be F1 cos 37. The component here is F1y. The component here is F2x. And the component here is F3y. If I calculate the values, then F1x is F1 cos 37. F1 is 10, cos 37 is 4 by 5. So it comes out to be 8 Newton. If I want F1y, F1y is F1 sine 37. F1 is 10, sine 37 is 3 by 5, which is 6 Newton. Similarly, F2x is F2 cos 45. So F2 is 5 root 2, cos 45 is 1 by root 2, it's 5. F2y, it's F2 sine 45. F2 is 5 root 2, sine 45 is 1 by root 2, that's again 5. And this F3 is acting along y-axis, so no need to resolve this vector. This vector is acting along negative y-axis. You need not resolve this vector. The x component of F3 would be 0. The y component of F3 would be 1 Newton. This we have discussed in the last class. If a vector is acting along y-axis, then its x component is 0. If it is acting along x-axis, its y component. The next is step number 2. In step 2, next we can calculate net force along x-axis. See, along x-axis we have two vectors, a vector F1x and a vector F2x. This F1x and F2x are acting in exactly opposite directions. So you can calculate net force along x-axis as the difference of f1x and f2x. Now, this is f1x and this is f2x. We always subtract greater from smaller. So this will be, it's f1x minus f2x. So force along x-axis is 8 minus 5, which is 3. This is fx, which is 8 minus 5 equal to 3. Similarly, you can calculate fy. Step 2 says net force along x-axis. In step 2, we will calculate net force along x-axis, which is 3 Newton. Similarly, we can calculate net force along y-axis. Net force along y-axis. F1y and F3y, they're acting in same direction, so they will add it up. But this F3 is acting in exactly opposite direction, so it gets subtracted. So you can write that net force along y-axis is, it's F1y plus F3y minus, so you can write your F3, F1y, your F1y, F1y, F1y is 6 Newton. F3y, not just F3y, it's F2y, sorry. F2. F2y. How much is F2y? That's 5. Minus F3, since it's acting along negative y-axis, it's 1. So 10, 11, it's 10 Newton. So this is the force along x-axis. This is the net force along y-axis. So the next task is to calculate this fx and fy. Say fx is acting along x-axis. Fy is acting along y-axis. This is fx. This is fy. And the angle between them is 90 degrees. So this is how you can calculate net force. This is net force. Fx, Fy, net force is F0. So the net force F is vector sum of Fx and Fy. So the net force F is, if you are adding Fx and Fy, it's root over Fx square plus Fy square. So the net force F is, it's root over Fx. How much is Fx? Fx is 3 Newton. It's 3 square. Fy, it's 10 Newton, it's 10 square. So F is 100 plus 9, that's root over 109. This is how we are calculating the net force F, which is root over 109 Newton. After this net force, this is net force F, which is root over 109. We also have to calculate the direction. For direction, we can calculate tan beta, perpendicular by base, right? So that's Fy divided by Fx. So your tan beta is Fy. Fy is 10, Fx is 3. So beta is tan inverse 10 by 3. This is the value of beta, which is tan inverse 10 by 3. There's one more topic, small topic, resolution of vector in 3D. Resolution of vector in 3D. When we resolve vector in 3D, this is x-axis, this is y. I'm sorry, I need x, y, and z all. This is x-axis, this is y-axis, and this is z-axis. Up to the last section, we have resolved vector in 2D along x and y axis only. But now we will resolve vector in 3 dimensions, x, y, and z axis. So if I call this as vector A, this vector A, it's making an angle alpha with the x-axis, it's making an angle beta with the y-axis, and it's making some angle gamma with the z-axis. This vector A, which is making angle alpha, beta, and gamma with x, y, and z-axis. So the component of vector A along x-axis, which is ax, is a cos alpha. Component of vector A along y-axis is ay, which is a cos beta. Z along component along z-axis is az, which is a cos. So these are the components of vector A along x-axis, y-axis, and z-axis respectively. These are the components. I can write this as even this ax is a cos alpha. You can write your cos alpha here as this is ax by a. That's first equation. Your ay is a cos beta. So your cos beta is ay by a. That's second equation. Similarly, you can write your az as a cos gamma. So you can write your cos gamma as az by a now. That is equation number 3. So this is how we calculate cos alpha, cos beta, and cos gamma. And this cos alpha, cos beta, and cos gamma are known as direction cosines. They are known as direction cosines. Cos alpha, cos beta, and cos gamma are known as direction cosines. The next thing is, you can write your complete vector in this form. This A is ax I cap, ay j cap, plus az k cap. So this is how we resolve vector in 3D. While resolving vector in 3D, you need angle with respect to all directions. You need angle with respect to x-axis, as well as angle with respect to y-axis, and angle with respect to z-axis. And similarly, you can have cos alpha, cos beta, and cos gamma components. You can write your total vector as ax I cap, ay j cap, az k cap. You can even write this as magnitude of vector A as its root over ax square plus a y square plus a z square. So this is the magnitude of vector A, which is root over ax square, ay square plus az square. There's one important thing. If I square and add these direction cosines, cos square alpha, cos square beta, and cos square gamma, it comes out to be 1. Simple calculation. Cos alpha is ax by a, so you can write this as ax square by a square. Cos beta is ay by a, you can simply write this as ay square by a square. Cos gamma is az by a, you can simply write this as az square by a square. It comes out to be 1. Next, you can take this a square as LCM, and you are left with ax square, ay square, plus az square, which comes out to be 1. And if I see root over ax square plus ay square plus az square is magnitude of a. So ax square plus ay square plus az square. Can I write this as a square? I'm writing ax square plus ay square plus az square is a square. The reason is this is the magnitude. You can represent your magnitude either in modulus, or you can simply write this as a or mod. I'm writing this a square by a square, which comes out to be. So this is what we were supposed to prove, that cos square alpha plus cos square beta plus cos square gamma is 1. So that was about vectors. So in circular motion, starts with the concept of, say, firstly the introduction of circular. Let's say you have a body. This body is moving on a circular track. It's revolving on this circular track. So up to now, whatever we have studied in motion in kinematics, in those body was moving in a straight line. But now your body will move on a circular track. So we'll have analog. Like in straight line, we have done studied displacement. But instead of displacement, now we will do angular displacement. Now we will do angular displacement. Earlier we did velocity, but now we will do angular velocity. Earlier we did acceleration, but now we will do angular acceleration. We'll do angular acceleration. So now onwards, we will study the motion of a body moving on a circular track. Let's start this thing with angular displacement. Start this thing with angular displacement. Let's say you have a body. This body is moving on a circular track. Let's say it's traveled from point A to point B. This is moving in this way. This is the center of the track. And this is the radius of track, right? This is the radius of track. This angle is theta. Or let's say delta theta. This angle swept by the radius vector is known as angular displacement. While moving from A to B, the angle which this radius vector sweep, like earlier radius vector is in this direction, then after covering an angle delta theta, it comes in this direction. So the angle swept by the radius vector is known as angular displacement. So angular displacement is the angle swept by the radius vector. So the angle swept by the radius vector is known as angular displacement. This angular displacement is an axial vector. Since body is moving on a circular track, so we call this as axial vector. Its direction is along the axis of rotation. Say body is moving in clockwise sense. So the direction of angular displacement will not be clockwise. Its direction will be along the axis of rotation. It's revolving about point O. So you can assume there is an axis which is passing through point O. This axis could have two directions. It can either come out of the screen or it could be into the screen. I'm repeating it again. Angular displacement is a vector, but it's an axial vector. Axial vector means these vectors have directions along the axis of rotation. This is the axis of rotation about which this is revolving. So this axis of rotation could have two directions. It can either be out of the screen or it could be into the screen. Whether it is out of the screen or into the screen, that direction is given by right-hand thumb rule. As an axial vector, its direction is along the axis of rotation, along the axis of rotation. It is given by right-hand thumb rule. It is given by right-hand thumb rule. This is axial vector. Its direction is along the axis of rotation and its direction is given by right-hand thumb rule. This is what we call axial vectors. So if I apply right-hand thumb rule here, see how to apply right-hand thumb rule. Right-hand thumb rule. To apply right-hand thumb rule, just take your right hand and curl your finger along the motion of body. Take your right hand and curl your finger along the sense of motion. If it is moving clockwise, just curl your finger clockwise. Where is the thumb pointing? Inwards. Curl your finger along the motion of body. Thumb will give direction of angular displacement. So just take your right hand, curl your finger along the sense of motion of body. This thumb will give the direction of angular displacement. That's right hand. Its SI unit is radian. SI unit is radian. This is the SI unit of angular displacement. It's radian. Is it clear, everyone?
Yes, sir.
Sure. So this angular displacement, we will use this angular displacement as frequent as we have used displacement in kinematic straight line. It's a relation between angular and linear displacement. Angular and linear displacement. So let's say a body is moving on a circular track. This is point A and this is point B. It moved from A to B. While moving from A to B, this is the radius. It covered an angle. I call this angle as d theta. So the angular displacement is d theta. Is there any linear displacement here? No. Is there any linear displacement here? Body is moving on a circular track. It moves from A to B. The angular displacement is d theta. Is there any linear displacement here? So there is one linear displacement in straight line from A to B. I call this as dl. Now we are supposed to relate this dl, this d theta and this r. To relate this d theta, dl and r in vector form, I can simply write dl as r d theta cross r. It's cross product of d theta and r. If you curl your finger clockwise, the thumb will move inside. This d theta is inverse. This d theta is inverse. And this is your radius vector r. This is your radius vector r. This d theta is inverse, r in the plane of board. What's the angle between d theta and r? Say I take this vector. This is inverse. Huh? And then I take this plane. My hand is another plane. This is my hand and this is the vector. What's the angle between my hand and this pen?
90 degrees.
90. Your d theta is acting in inverse direction. Your d theta is inverse into the plane of board. This inverse direction is your d theta. And your r is in the plane of board. So can you see these two things are perpendicular to each other? This direction and this direction. So can I write this d theta? Now, if I open this cross product dl, so how you open a cross product? A cross B is AB sine theta.
D theta
Right.
into
Yes.
R
Right.
into
Yes.
sine 90. That is 1.
So d theta, dl is r d theta. This is the angle between linear and angular displacement. Whenever you have angular displacement, there is a linear displacement attached. And you can calculate linear displacement as r into d theta. Or this is in the vector form. The direction of linear displacement is tangential. Tangential to the circular path. Okay, after relation between angular and linear displacement, the next thing is angular velocity. See, just like linear velocity, angular velocity is the ratio of angular displacement and time. We represent angular velocity with omega. Angular velocity is the ratio of angular displacement divided by time. This is angular velocity. Ratio of angular displacement and time. Ratio of angular displacement and time. This angular velocity is again an axial vector. So if it is an axial vector, its direction is same given by right hand thumb. Whenever I say it's axial vector, the direction is same as that of angular displacement. It's average. This is average. When you take delta theta by delta t, this is an average. This is average. Whenever you use delta, the quantity that you got is average. For instantaneous, omega, we take d theta over dt. For instantaneous value, we always differentiate. For average, we take ratio. This is instantaneous. This is what we did in velocity and speed too. The average speed was the ratio of displacement and time. But for instantaneous, we differentiated it. So it's instantaneous. We are using differentiation. Its SI unit is radian per second. The SI unit is its radian second inverse. This is it. The next is relation between angular and linear velocity. So linear and angular velocity. So if a body is moving on a circular track, it's moving in this way. This is the direction of angular velocity. It's moving in this way. This is angular velocity. If you want linear velocity, then the direction of linear velocity would be same as that of linear displacement. What was the direction of linear displacement, Noor? Body is moving on the circular track. What was the direction of linear displacement?
A to B.
Linear displacement was tangential, right? Your linear velocity will again be tangential to the circular track. The direction of linear velocity will always be tangential. Linear velocity will always be tangential to the circular track. This is the direction of linear velocity, which is always tangential to the circular track. So you can say that linear velocity is tangential to the circular track. This is the direction of linear velocity. It's always tangential to the circular. And you can relate linear velocity and angular velocity in this way. So if you look at the pattern, linear displacement is d theta cross r. If you remember this pattern, you can relate linear and angular velocity, linear and angular acceleration. Like linear displacement is angular displacement cross r. So you can write this as linear velocity is angular velocity cross r. So v is omega cross r. This is the linear velocity, omega cross r. This is it. That's the relation between linear and angular velocity. See here, omega and r are perpendicular. Just like d theta and r are perpendicular, your omega is perpendicular to r. So if I open the cross product, it comes out to be its omega r sine 90. And it comes out to be omega. So I'm repeating it again. Linear velocity is always tangential to the circular path. Its magnitude is just omega angular velocity multiplied by the radius of the path. The next thing is a body revolving cover 10 radian in 2 seconds. On a circular track of radius 5 meters. Calculate first part. It's angular velocity. Angular velocity. Second part. Linear velocity. It's a simple formula based numerical. Angular velocity is angular displacement over time. Your angular displacement is 10 radian, time is 2 seconds, so it's 5 radian per second. The second one is linear velocity, which is omega into r. So that's omega, which is 5, multiplied by r, which is 5. So linear velocity comes out to be 25 meters per second. Is the linear velocity. The next thing is uniform circular motion. So uniform circular motion means circular motion with a constant speed. It means motion with a constant speed. Motion with a constant speed is known as uniform circular motion. Say this is a circular track. This circular track. Over this circular track, a body is moving. Body is moving on this circular track with a constant speed. Like the magnitude of speed is always 2 meters per second. Here again, the magnitude of velocity, constant speed, or constant magnitude of velocity. Constant magnitude of velocity. The direction of linear velocity is changing continuously, but the magnitude remains constant. Magnitude does not change. So these types of motions are known as uniform circular motion. So in uniform circular motion, the speed, the magnitude of velocity will remain constant, but its direction will change continuously. These types of motions are uniform circular. So in uniform circular motion, first of all, magnitude of linear velocity is constant. Magnitude of linear velocity is constant. And remember, what was acceleration? Acceleration was rate of change of velocity. If velocity changed, then acceleration come into play. So if magnitude of velocity changed, then you will have one acceleration. But since magnitude is not changing, that means no acceleration. No acceleration due to change in magnitude. See, in uniform circular motion or in circular motion, we have 4 parameters that need to be checked for acceleration. The first parameter is magnitude of linear velocity. The magnitude of linear velocity, if it is constant, then there is no acceleration. But if the magnitude of linear velocity change, then you will have an acceleration. Similarly, the second one is direction of linear velocity. If direction of linear velocity changes, then you will have a corresponding acceleration. If it doesn't change, then no acceleration. The third parameter is magnitude of angular velocity. If magnitude of angular velocity change, then you will have a corresponding acceleration. The last one is direction of angular velocity. If direction of angular velocity change, then you would have a corresponding acceleration. So the first term, magnitude of linear velocity is constant, no acceleration. What about direction of linear velocity? Is it constant or it's changing? It's changing. Direction of linear velocity is changing. Direction is changing. That means you will have an acceleration. You will have an acceleration which is known as centripetal acceleration. You will have a centripetal acceleration. Third part. After direction of linear velocity, if I talk about angular velocity, see V is omega r. So your omega is V by r. You can check directly that if V is constant, R is constant, that means omega is constant. Magnitude of angular velocity is not changing, it's constant. Magnitude of angular velocity is constant. Angular velocity is constant. If it is constant, that means no corresponding acceleration. No acceleration. Fourth one. The direction of angular velocity, just curl your motion. The body is moving clockwise, just curl your finger clockwise. This thumb will give the direction of your angular velocity. Your body is moving clockwise, just curl your finger clockwise. Your thumb is moving in inverse direction. It's always inverse. So direction of angular velocity is not changing. It's moving on circular track, it's clockwise. The direction is not tangential. For angular velocity, the direction is along the axis of rotation. So just curl your finger along the sense of rotation. This thumb will give the direction of angular velocity. Direction of angular velocity is constant, does not change. Is constant. That means no acceleration again. So if you study uniform circular motion, there is only one quantity which is changing, and that one quantity is direction of linear velocity. So you will have just one acceleration, which is known as centripetal acceleration. In uniform circular motion, we just have one acceleration, known as centripetal acceleration. Centripetal acceleration is very, very important. You will use this in laws of motion, even in gravitation. You can't do gravitation without having knowledge of centripetal acceleration. Because in gravitation, everything is revolving. Planets are revolving around the sun. Moon is revolving around the planet. So there, this centripetal acceleration will come into play. The next is centripetal acceleration. So what's the cause of centripetal acceleration? Why it arises in circular motion? Linear velocity, change in direction of linear velocity. While doing circular motion, should be very precise that acceleration is coming due to change in magnitude or due to change in direction. The centripetal acceleration, it arises due to change in change in direction of linear velocity. Direction of linear velocity. So this is simply just due to the change in direction of linear velocity. Due to change in direction of linear velocity, you would have centripetal acceleration. So if a body is moving on a circular track, this is point. This is the radius of the track. Velocity is always tangential. This is the velocity. This is the velocity. This is always tangential. So due to change in direction of velocity, centripetal acceleration arises, which is v squared by r. Or in terms of omega, you can write this as omega squared r. This is centripetal acceleration. The cause is change in direction of linear velocity. The direction of centripetal acceleration is always towards the center of r. Direction of centripetal acceleration is always towards the center of r. Direction of centripetal acceleration is always towards the center of circular path. This is the direction of centripetal acceleration. And its magnitude is v squared by r, or you can simply write this as omega squared r. Changing. Say if the particle is here, then the center is acting towards the center in this direction. The particle is here, acting towards the center in this direction. See, direction is changing. If particle is here, then the centripetal acceleration is upwards. If the particle is here, then the direction of centripetal acceleration is downwards. Although it's always towards the center, but it's changing continuously. If the particle is here, then the towards the center is downwards. If the particle is here, then the towards the center is upwards. The direction of centripetal acceleration is continuous.